Hello, calculus class. Welcome to the very first remote lesson in this age of online learning for the next few weeks. So today we're going to sort of see something that should look pretty familiar. You can see the aim up on the board or the screen. It says, how can we solve separable differential equations? So basically, the goal for the day will be to answer a question like this. So take a moment and read through it. A lot to unpack, but we'll eventually get there. So just give it a read, pause this, and I'll return in a bit. All right, so assuming you paused and read through this, you'll notice there's a lot of information given. The first sentence deals with sort of a position function, right? The baseball is thrown upward from the roof of a 100-meter high building. So we know that the initial position of the baseball is 100 meters off the ground, and then 8 seconds later it is on the ground, right? So those are both position information. And then we're given an acceleration function. And then we are told that we're interested in some information about the velocity function over here. All right, so this is something we've seen. It's similar to rectilinear motion, where you have a series, a system of position, velocity, and acceleration functions. All right, we'll eventually get to solving this question in a moment, or in many moments. First, I want to go through some examples, some warm-ups, blah, blah, blah. So here's a do now question. I'd like you to give it an attempt. So again, please pause, try it out on your own, and then press play again. All right. Okay, welcome back. Assuming you went ahead and attempted this problem. So basically we're given dy dx equal to 4x to the 7th, and we're trying to solve for y being a function of x. So we're given a derivative function, and we're asked to solve for the original function. So you can think of this as the same relationship as, we're given acceleration and we're asked to solve for velocity, or you're given velocity and you're asked to solve for a position function. So there are a couple of ways of going about this. This is known as a differential equation, right? And we've heard this term before. A differential equation is where you're given a derivative and you're actually asked to solve for a function. You're not solving this equation for a number, you're solving it for a function. Okay, so the next slide here, I'm just showing you the steps of the work involved. Of course, if we're given a derivative and we're asked to solve for y, well, if we're given y prime and we're asked to solve for y, then we want the antiderivative. So that means we need to integrate. And since x is the independent variable here, we're going to integrate dx. So we have an equation. Of course, with any equation, whatever operation you perform on one side, you must also perform on the other side. So the operation I'm going to perform is integration with respect to x. So that's why I have the integral symbol dx here. All right. And so I apply that operation to both sides. Integral dx, both sides. After sort of simplifying a little bit, the left side is just the integral dy, and that should be equal to the integral of 4x to the 7th dx. Integrating the left side dy, you get y plus c1. Integrating the right side dx, you get x to the 8th over 2 plus c2. So those are, that's just the power rule on the right side. And notice that I have c1 and c2 because these are potentially two different constants. I don't know what they are. We know that there exists some constant on the left side, some constant of integration on the left side, some constant of integration on the right side. Moving forward, again, remember the goal is to solve for y, so I'm going to isolate y. And so I can express the equation as y equals x to the 8th over 2 plus the quantity of C2 minus C1. But typically, though, we actually, instead of writing it as C2 minus C1, think about it. If I take a constant and subtract a constant from it, I get another constant as a result. So really, most of the time, in fact, all of the time, I'm totally fine with you just expressing your final answer as y equals x to the 8th over 2 plus just c. No need for a subscript in this case, since we're combining the constants, and again, adding and subtracting constants together just give you another constant. In this situation, this is called a general solution. Okay, so we've solved an equation, and we have basically a function, but really we have a family of functions, because depending on what the value of c is, the graph is going to look slightly different. In this particular case, since we're adding c to the term x to the 8th over 2, this constant will act as sort of a vertical shifter. So the curve will either be shifted up or down depending on the value of c. All right. I just want to show you sort of like a shorthand way of solving the same exact problem. So you might notice over here that this kind of looks like, a ratio equals some other ratio. Imagine this is over 1. And when you were in algebra and you were solving problems like these, you remember you did an operation called cross multiplication. All right, so we can separate the differentials in this particular case and put all the x's on one side, x's and dx's on one side, and all the y's and dy's on the other side. And this is why these types of problems are called separable differential equations, when you can easily separate the differentials so that all x's and dx's are on one side and all y's and dy's are on the other side. We call those equations separable differential equations. Anyway, when you get to this point, you have dy is equal to 4x to the 7th dx. Apply the integral operation on both sides, and you can see that we are at the same point we were in the previous slide, right? And so from there, everything is exactly the same, and we end up, of course, in the same exact spot. I just kind of wanted to show you the shortcut of cross multiplication to make your life a little bit easier. All right, so moving on, let's try one more together. So this problem, a little bit more complicated. Dy over dx is equal to x times y to the negative 1. Again, what is y equal to? So we're still solving for y. So first step, I just actually re-expressed it equivalently. So dy over dx, that didn't change, but x times y to the negative 1, I could actually, of course, rewrite as x over y. And now this gives me a nice natural way of separating the differentials. So again, cross multiplication leads me to an expression that says y dy is equal to x dx. Oops. And then, of course, what I'll do next is integrate. All right, so integrating the left side dy, I get y squared over 2. In integrating the right side, I get x squared over 2 plus c. Now you'll notice that I guess I should technically, let me change the color. I should technically have a plus c1 here, and this should be a plus c2. But like I said previously, all I'm going to end up doing, since I'm isolating for y anyway, all I'm going to end up doing is subtracting that c1 over to the right and combining the two constants into one big constant. And so just to save time, I just did that already. All right, so I just rewrote it as y. I expressed the solution, or this step of the solution, as y squared over 2 is equal to x squared over 2 plus c. And you can feel free to do that. And okay, continuing, solving for y, this becomes y squared is equal to x squared plus c, multiplied by 2 on both sides. And you also might notice again, okay, if I multiplied by 2 on both sides, shouldn't it technically be a 2c over here? Yes, you're right. It should technically be a 2c. But again, if c is a constant, and if I multiply that constant by 2, I have, again, a constant. So it's totally fine for you just to express it as c. Okay? Now moving forward, solving for the general solution. Again, general solution is just isolating y so that you have it written as a function of x. Since we're applying the radical to both sides, I should have a plus or minus operator at the front of the right expression. Okay, and so this is your general solution. Both of these branches are part of this general solution. And one interesting thing is that this c is no longer going to act as just a vertical shifter, because this c isn't just simply being added to the function x. It's actually underneath the radical, so it's part of the function itself. And so I just want to show you a few slides for different values of c, which show how c actually affects this curve. Again, it's not just a simple vertical shifter as we're used to. So here is, by the way I get these graphs, I use a website called Desmos, Desmos. Strongly recommend it if you want to sort of get a sense for what these functions look like, and if you want to test out different values of c. Very nice website, Desmos. Anyway, this is what the curve looks like, the curve that we just solved for. This is what it looks like when c is 0. All right, kind of interesting. If you simplify it, it's just the lines y equals x and y equals negative x. So kind of makes sense. For c equals 1, kind of looks like this. You might recognize this as a hyperbola, and indeed that's what it is. And for c equals negative 1, the curve looks like this. So these are all actually hyperbolas, just for varying constants. All right. The next step in a question like this, so we've been finding the general solution, but really what most problems are interested in are a particular solution. So we want a specific function that satisfies a condition. So again, we'll be given a differential equation, but we'll be given more information which tells us, where this differential equation curve should pass. And in this case, this curve should pass through the point 0, 3. All right? So basically, we start off with the general equation that we solved for earlier. No need going through and solving that same problem again. But the thing here is, I want you to notice that the point that we want to travel through, oh, that was a terrible line. Okay, the point that we want to travel to has a positive y value, positive 3. So rather than focus on y equals plus or minus radical x squared plus c, I'm only going to focus on the positive branch because I know my y value has to be positive. Okay, so I'm just going to use the positive branch, and now I will plug in the information embedded into these coordinates. So the y is 3, x is 0. Solving for c, you get that c is equal to 9. So to write down our final answer, which is called the particular solution, that would be y equals positive radical x squared plus 9. All right, and again, when you're writing your particular solution, you don't want to use plus minus. You want to use whatever branch actually went through the point 0, 3 in this case, and that's the positive branch. To show you a nice diagram, I went into Desmos, I sketched y equals radical x squared plus 9. This is the curve we end up with, and as you can see here, this curve is most definitely passing through the point 0, 3. All right, so we have solved the problem. All right, great. So these are just sort of some warm-ups. Let's now attack and unpack that beast of a problem from the beginning slide. So just a reminder, we are supposing that a baseball is thrown upward from the roof of a 100-meter high building. It hits the street below 8 seconds later, assuming a system where acceleration due to gravity is negative 9.8 meters per second squared, and assume there's no air-wind resistance. Let's make this simple. What was the initial velocity of the baseball, and how high did it rise above the street before beginning its descent? So essentially, we're given a bunch of information. We're given the acceleration function, and that's a constant. We're given the initial position function. So let's call S of t the position of the baseball above the ground at any time t. We're told that S of 0 is 100 meters, and we're told that S of 8 is 0 meters. Right, what exactly do we want? Well, we want the initial velocity, right? It says explicitly what was the initial velocity of the baseball. And we also want the maximum position. So maybe it's not very clear, but the question does say, how high did it rise above the street before beginning its descent? That's just a fancy way of saying what was the maximum position. So max S of t. So let's start out with the first problem, v of 0. Well, first of all, in order to solve either of these problems, we should probably take our acceleration function and solve that differential equation for the velocity function and the position function. And I'm going to do what we did in the previous two slides, right? So I know that if I have acceleration and I want velocity, I'm just going to integrate that acceleration function with respect to the independent variable, which in this case is time. So I will integrate acceleration dt, and of course that gives me negative 9.8 times t plus some constant, c1. And I'm going to leave the subscript there in this case, and hopefully you'll see why. All right, but that's my velocity function. But and again, this is just the general solution for velocity, not the particular solution yet. So we have not applied any of our initial conditions. And that's fine, we will eventually. But for now, let's just leave it with our general velocity equation. Moving on, I could take that general velocity function and integrate it to get my general position function. So if I integrate negative 9.8t plus c1 with respect to time, I end up with negative 9.8t squared over 2 plus c1 times t. So that constant, when integrated, now has a t factor attached to it. And then, of course, the position function has its own constant c2. Right? So there are two separate constants in this case, and I can't combine them this time because there is that t factor attached to c1. So it's like if I wanted to add 3x plus 2, I can't just say, oh, that's 5x, right? I cannot combine these terms. So moving forward, now that we have our general solutions, now is the time that we're going to go ahead and apply our particular solutions. So we'll use the particular information. My initial condition is that S of 0 equals 100 and S of 8 equals 0. You can see that if I take my general position equation and plug in 0, I'm going to end up canceling out two of the terms, this term and this term. So that will help me easily solve for C2. So I use that I use that initial condition, and I solve for C2, and that tells me that C2 is 100. Okay, nice and simple. So now let's update our general solution. I now have, instead of plus C2, I have plus 100. I'm now going to use the second initial condition, or maybe in this case is like the final condition. So S of 8 is equal to 0, so I'll just plug in or substitute where appropriate. And the algebra tells me that my constant 1 is 26.7. So again, moving forward and updating both velocity and position functions, I now have particular solutions for both velocity and position, right? That C1 was a constant in v of t and s of t, and also C2 was a constant in s of t. So I've solved for both of them, and now I have actually particular solutions for velocity and position. So I realized that I did not actually find the initial velocity, but that's simple. We just simply take our velocity function, plug 0 in, and you get 26.7 meters per second. So there you have the initial velocity. The second part of the problem, of course, is to maximize position. In order to maximize position, really remember, anytime you're maximizing a function, you want to take the derivative of that function and find its critical points. So set it equal to 0 or find where it's undefined. In this case, the derivative of position is velocity. So I'm going to take my velocity function, set it equal to 0. It cannot be undefined, so I'm not going to worry about that. But velocity is equal to 0 when t equals 2.724 seconds. Now, this does not guarantee that this is a maximum. This is just a candidate for a maximum. So I need to confirm. And this is one area where like a lot of students they'll solve for this value of t and just stop assuming that this is definitely the maximum. We have to confirm. And since this is a system on a closed interval from t equals 0 to t equals 8, the way we're going to confirm is by using the table of values and all of our candidates. So the endpoints are candidates and the critical points are candidates. Our endpoints are 0 and 8. Our critical point was 2.724. I'm going to take those time periods and plug them into the position function, and you'll see that you end up with 100 meters, 136.372 meters, and 0 meters. So this does confirm that when t equals 2.724 seconds, the maximum position occurs, and that is 136.372 meters. Okay. All right, so I think that's all for this sort of PowerPoint presentation. I hope this kind of helps you work through the classwork/homework that I'll be posting. If you have any questions, please present or post them on Google Classroom. My idea is to sort of post YouTube videos like this pretty regularly. If it works out, if not, I mean, if we decide that this just isn't quite working out, we'll try something else. But for now, this seems like it could be fun, and I think it could be pretty good. I think you might enjoy this. So anyway, let me know, give me feedback, and we'll figure it out together. All right, ladies and gentlemen, I hope you enjoyed. See ya.